All right, guys. Welcome to our week 7 AP Physics 1 content review. We are starting here at 10 o'clock. Please make sure you mute your microphone and turn off your webcam. Feel free to unmute if you have questions. We want you to ask them if you have them. We are recording this session today, and that recording is going to be posted on the A+ College Ready Science YouTube channel. You'll find lots of videos there that might help you in this course. Next week's week 8 session will be held on Thursday, October 16th. Also at 10 o'clock, and your teacher will have the join link for that session. So I hope to see you there. Today we're going to talk more about forces and dynamics, and we're just going to start off with some practice problems. So this one says a push mower of mass M is pushed along a flat frictionless surface. So no friction. Let's just kind of draw this out. So here's our push mower. The angle of the handle is at a 60-degree angle above the horizontal. So let's just kind of draw in a horizontal right here. And this angle, 60 degrees. The angle of the handle is then lowered to a 45-degree angle above the horizontal. If the same force is applied along the handle, the magnitude of the horizontal acceleration of the mower is. So we're applying a force this way along the handle. What you've got to realize is what's causing the acceleration is the horizontal component of F. So let's take this F and let's draw down a vertical here on the handle, and let's break that up into a horizontal component. We'll call that FH, and a vertical component. So the vertical component of that force is just pushing the lawnmower against the ground. The horizontal component is pushing it across the ground and causing it to accelerate. Since there's no friction, this force is going to be the net horizontal force, and it's going to cause the acceleration. So what we've got to figure out is which one of these is going to cause a bigger horizontal component, an angle of 60 degrees or an angle of 45 degrees. So to do that, let's use the cosine function, since this is the adjacent side to the angle. And let's say the cosine of 60 equals adjacent FH F sub H over the hypotenuse, which is our F. And let's do the same with the 45. Actually, let's solve that out. So FH is going to be equal to F times the cosine of 60. And that would be the same if the angle was 45. So what we really need to know is the cosine of 60 or the cosine of 45, a bigger number. Some of you may have those memorized. The cosine of 60 is just 1/2. And the cosine of 45 is square root of 2 over 2, which is 0.707. So the cosine of 45 is a bigger number. Therefore, the horizontal component is going to be bigger at 45 degrees. And so our answer is going to be, when we move the angle of the handle down to 45, the acceleration, the horizontal acceleration of that lawnmower is going to increase. I think we've pretty much already answered question 2. We want to know in this one, same problem, the horizontal acceleration of the lawnmower in terms of F when the handle is at 60 degrees. So let's sketch that out again real fast. So we're applying F along the handle. First of all, let's find the horizontal component of the force. And we already did that a minute ago. We called that FH. And we said that the cosine of 60 equals the adjacent side FH over the hypotenuse F. So FH equals F cosine 60. So that's the horizontal component of the force, which is the net horizontal force since there's no friction. So that's F net. And we know that acceleration equals F net over m. That's Newton's second law. So in this case, the acceleration would equal the F net, which is F cosine 60 over the mass, which we don't know. We just know it's M. So our answer is going to be B in this case. All right, so these next 5 problems come from a website called learnaphysics.com. If you're looking for some good practice problems that are very AP-like in style, I would highly recommend you go to that website, and you'll be able to find lots of good practice problems. So here's the first one. 3 blocks of mass M, 2M, and 3M are placed adjacent to each other on a frictionless, keyword frictionless, horizontal surface as shown. A constant force of magnitude F is applied to the right. So as you see here, we're pushing on the box M with a force of F. Which of the following statements is true? The acceleration of the blocks will vary according to mass. Well, if we're pushing on box M, they're all going to accelerate. They're all going to have the same acceleration, right? So it's definitely not A. The acceleration of each block will be the same. That's true. But it's not going to be F over M. It's going to be acceleration equals F net over M. Here we're thinking about the system. So the acceleration of this system is going to be the net force, which is F, over the total system mass, which would be 6M. That's what our acceleration actually is going to be. The net force acting on each block is the same. Well, that's not true either, because the net force acting on, for example, box number M, let's just draw a free body diagram for box M. So box M has a gravity force acting down. It has normal force acting up. It has this force of F pushing it this way, but there's also a force of box 2 on box 1. Box 2 is pushing back on 1. So we'll call that the force of 2 on 1M. And that's that. So these components are going to be similar. Well, let's just go ahead and do a free body diagram for the 2M box. So this is box 2M. Again, force of gravity, normal force. In this case, there's going to be a force of box M on box 2M, pushing it to the right. But there's also a force of box 3M on 2M, pushing it to the left. So notice the net force on each of the boxes is going to be different. So C, not the same. B, not correct. The magnitude of the force on block 3M from 2M is greater than the magnitude of the force back on 2M from 3M. So that statement there completely contradicts Newton's third law. However hard 3M pushes on 2M, 2M has to push that hard back on 3M. So this one's just dead wrong. It goes against Newton's third law. So let's look at E. The net force acting on block 3M, is 3 times the net force acting on M. Well, we just got through saying that their accelerations have to be the same. If their accelerations are the same, and this one has a mass 3 times this one, then the net force acting on this one has to be 3 times the net force acting on this one. Otherwise, their accelerations won't be the same. So E is our correct answer. All right, so here we have a graph of force against time. It says a block is pushed along a horizontal frictionless surface with a horizontal force that varies as a function of time as shown in the graph. So again, horizontal frictionless surface. So at time 3 seconds, the acceleration of the block is 5 meters per second square. Find the mass of the block. So let's think about Newton's second law. Since there's no friction, the horizontal force shown by the graph is going to be our net force. We're trying to find the mass. So let's go ahead and solve Newton's second law for mass. So mass is going to be equal to F net over A. So let's go over to 3 seconds. And let's cut up and cut over. The force at 3 seconds is 15 newtons. That's the net force at that instant in time. And the acceleration at that instant in time is 5 meters per second square, which means the mass at that second in time has to be 3 kilograms. So we're looking at answer C. All right, so here's problem 5. A mass of 10 kilograms is suspended from a cable, A, and a light, rigid horizontal bar that is free to rotate as shown. What is the approximate tension in newtons in the cable? All right, so let's think of this as the tension, this part, what we're calling A. And let's take this and let's divide it into components. So let's draw a vertical down right here. And a horizontal right here. This vertical component has to support all the weight of this box because this horizontal piece doesn't have a vertical component. So all the weight is supported here, which means this side has to be equal to 10 times 10, mass times acceleration due to gravity. So the weight equals mg. So this is 100 newtons. Now we can solve for tension by using a trig function. We can use sine, and we can say the sine of 60 equals the opposite side, which is 100, so this way, over the hypotenuse, which is the tension force, which means tension is going to equal to, let me just 1 second here, guys, something's not right. Tension is going to be equal to 100 over the sine of 60. And let's check that out. 60 sine 0.860, 100 over 0.866. Let's solve that out. So that comes out to be about 116. 116.28 to be exact. So we need to figure out which one of these is 116.28. A couple of ways we can do that. Let's just go through and check them. So let's go 100 divided by the square root of 3. So that is 57. 100 times the square root of 3. 173. 200 divided by the square root of 2. Nope. And 200 times the square root of 3. No. So let's see what I did wrong there. So let's say we said the sine of 60 equals 100 over tension. Tension equals. Okay, so yeah, I just miscalculated. So the tension is the sine of 60 is the square root of 3 over 2. So if we take 100 over the sine of 60, which is the answer we got, that's 100 over the square root of 3 over 2. We can flip that 2 up to the top. So it'd be 200 over the square root of 3. So I must have plugged some numbers into the calculator wrong there. All right, so now let's look at this one. The free body diagram shows all forces acting on a box supported by a stationary horizontal surface, where the length of each force vector is proportional to magnitude. Which statement below is correct? So we've got force of gravity and a normal force. Those cancel each other out. So we have a net force of friction acting to the left. So this frictional force is the net force. So the box is moving to the left due to the force of friction acting in that direction. Well, remember that friction always acts in the opposite direction of motion. So the friction can't be acting to the left if the box is moving to the left. So A, not correct. The box must be accelerating to the right as indicated by the force of friction in the opposite direction. Well, we just got through saying that the net force is the frictional force, and it's acting to the left. Acceleration always happens in the direction of the net force, which means B cannot be right. The box is moving to the right as indicated by the force of friction in the opposite direction. This might be counterintuitive to some of you, but this is the correct answer. So think of it this way. Maybe you've pushed a box to the right, and it's sliding across a floor that's fairly slick. After that box leaves your hand, you're not applying any force to the right. The only net force acting on it is the net force of friction. So it's moving to the right, but it's accelerating to the left because there's a net force acting to the left, and that net force is the frictional force. So that's the situation we're looking at here, and that's why C must be correct. All right, so a block of mass m is placed on a plane inclined at an angle of theta relative to the horizontal. There's a coefficient of friction of mu k that acts as the block accelerates down the ramp. The acceleration of the mass is. So here's what we've got to do in a problem like this. You want to go to the center of your box, and you want to draw in a vector that approximates the weight. So this is mg. And then you want to take that weight and you want to divide it into components. One component that's perpendicular to the plane and one that's parallel to the plane. So let's draw down a line here that's perpendicular to our plane and one that's parallel to our plane, like so. And we're going to call this F perpendicular and this F parallel. And it turns out that if this angle here is theta, this angle is also theta, because the triangle I just drew and the big inclined plane triangle turn out to be similar triangles. So let's solve for F parallel and F perpendicular. In this case, F parallel is the opposite side to that angle of theta. So we're going to use sine, and we're going to say the sine of theta equals F parallel over mg, which means F parallel equals mg sine theta. F perpendicular is the adjacent side to the angle, so we're going to use cosine. And we're going to say the cosine of theta equals the adjacent side over the hypotenuse, which means that F perpendicular equals mg cosine theta. Well, it turns out in problems like this that the normal force is going to be equal to the perpendicular component of the weight, because this perpendicular component of the weight is how hard the box is pushing down against the plane. And the plane has to push back up with an equal and opposite force. So this is the normal force. This component, the parallel component, since there's no friction, or there is friction in this case, is the part of the force that's pushing the box down the plane. So let's think about this for a second. The net force in this case going down the plane is going to be equal to the force that's pushing it down the plane minus the frictional force that's pushing in the opposite direction, which means that the net force is going to be equal to F parallel, which is mg sine theta, minus the frictional force, which is, let's think back to our friction equation. That's our equation for the force of friction. So in this case, that's going to be mu sub k times n, and we established that n is mg cosine theta. So this is our net force. We know that acceleration equals F net over m. So let's take our net force, which is mg sine theta, minus mu mg cosine theta, and let's divide that by the mass. Mass is going to cancel here, here, and here. So our answer in this case is going to be g sine theta minus mu cosine theta, minus mu g cosine theta. So we're looking at answer E is our correct answer. Now, let's look at something else here. If in this case there had been, let's say there had been no friction between this plane and the box. So we draw in our weight, we find our components. So they drew the components on the opposite side, but same idea. So if there were no frictional force, this would be theta. Let me redraw the diagram. So I prefer to draw mine like this. So I'm going to draw in my weight. That's mg. I'm going to break it into components, perpendicular and parallel. Where if this is theta, this angle right here is theta. So my parallel component, I'm going to go sine of theta equals F parallel over mg. F parallel equals mg sine theta. So let's say there had been no friction. It's a frictionless surface. That means that the net force acting on this box is equal to F parallel, which means the acceleration is equal to F parallel divided by the mass. F parallel is mg sine theta. Mass is m. So when a box is sliding down a frictionless inclined plane, its acceleration is going to be g times the sine of theta, and that's kind of a famous physics equation. G sine theta is the acceleration of a box sliding down a plane when there's no friction. All right, so let's end today by looking at this free response question. So we have two blocks connected by a string. We're not negligible mass, so we're ignoring the mass of the string. We're ignoring the mass of the pulleys, and we're saying there's no friction. So there's a lot of things here that can't completely be true in this diagram. The mass 2 is greater than the mass of 1, and the blocks are released from rest. So the dots represent the blocks. Draw free body diagrams showing and labeling the forces exerted on each blocks. Draw the relative lengths of all vectors to reflect the relative magnitudes of the forces. So let's go to block 1 first. So on block 1, we have its weight acting down. So let's draw it like so, and we're going to label that as Fg. And then what the force we have acting up on it is the tension in the rope. The rope is pulling it up. So, and in this case, we know since block 2 is heavier than block 1, we know that block 1 is going to accelerate upward, which means that the tension has to be bigger than the weight of block 1. So let's draw this arrow up, and let's draw it a little bit longer than we drew the weight going down. We're going to call that Ft. All right, now let's go over to block 2. No, there's no horizontal forces, so that's it for block 1. For block 2, we have the weight going down. And first of all, I need to make sure I draw that longer than I drew the Fg for block 1 because it's heavier. And I also know that this block is going to fall down, which means that Fg here has to be bigger than the tension which is pulling up on it. It is important to note that the tension over here and the tension over here should be the same length. Again, no horizontal forces acting on these boxes. That's it. That's our answer to part A. Now, part B says derive the magnitude of the acceleration of block 2. Express your answers in terms of M1, M2, and G. First of all, let's think about what the net force is here. So the net force is going to be equal to M2G, the weight of block 1, minus the weight of block 2. I'm going to go ahead and factor out a G and write it this way. All right. And now that acts on all the mass. So we know that acceleration equals F net over M. So in this case, the net force is G, M2 minus M1. And that net force is acting on all of the mass of the whole system, which is M2 plus M1. that is going to be our acceleration of our system, and therefore the acceleration of each block, because each block has the same acceleration. They're attached together with a string. So that's what we're looking for as our answer to part B. Now, part B, in this case, we put block 3 up here right in the middle. There's no friction between block 3 and the table. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as the original 2-block system. Explain how you arrived at your answer. So let's go back to this work that I just did. So this was the acceleration of the system, and therefore the acceleration of each block. The net force acting on the system, whether there's a block right here or not, doesn't change. It's still the difference between this weight over here and this weight over here. So this part of our equation doesn't change. What does change is the mass of our system. That net force, if there's a block here in the middle, now acts on M2, M1, and M3, which means the bottom part of our fraction gets bigger, which means our acceleration gets smaller. So our answer here, the magnitude of the acceleration of block 2, the magnitude of the acceleration of the whole system gets smaller because the same net force now acts on more mass. And since A equals F net over M, if mass goes up and net force stays the same, then acceleration is going to become smaller. All right, that's it for our session today. We're almost finished with dynamics. We'll do a summary of dynamics next week, and then we'll move on to the next unit. Hope that helped. Hope to see you next week, next Friday, 10 o'clock. And again, your teacher will have the join link. Thank you.